All right, welcome to Chapter 2, Rate of Change Using the Derivative. Let's see, Section 2.1, Instantaneous Rate of Change. All right, so first term here, average velocity. We've talked about this before. Average velocity just means find the slope between 2 points, right? So here's a quick example. We throw a grapefruit straight up into the air. This table below, or the table below, gives its height y at time t. What is the velocity of the grapefruit at exactly time equals 1? So we use average velocities to estimate this quantity. All right. So here's the chart of the data, right? The average velocity on the interval from 0 to 1, right, from time equals 0 to time equals 1, is 84 feet per second. So again, you would just calculate the slope, right? So, think of this is your x value, right? In this case, it's a t value, but you have this coordinate point 0, 6, and this point 1, 90. And what you would do, of course, is calculate the slope using the slope equation we've used several times before now. So that average velocity is 84 feet per second, and the average velocity on the interval from 1 to 2 seconds, all right, use the same process, use those two coordinate points to find the slope, is 52 feet per second. So what do we expect? So we expect the velocity at time equals 1 to be between those two numbers right there, 84 and 52 feet per second. All right, suppose that we find the average velocities on either side of t equals 1 over smaller and smaller intervals, as in the figure below here. Okay, so let's do a quick example here, though. So let's decrease the amount of time. Instead of going, 1 second intervals, what if we went with a much smaller time interval? Let's see. So let's see. We're going to find the average velocity from time equals 1 to time equals 1.01. So 1/100th of a second later instead of 1 full second later. Okay? All right. So we're going to use from this data point to this data point, right? Okay. So let's do this. So delta y, the change in the y values, divided by the change in the time values. Again, this is just your slope equation. All right. So what this is, so using the notation up here, S of t, right? So S at 1.01 seconds minus S at 1 second. S is the position. 1.01 minus 1. All right, so we calculate this again. We're using those data points down below that I circled. All right, so we've got 90.678 minus 90 over, and then 1.01 minus 1 is 0.01. All right, so if you punch that in your calculator, now when you punch that in your calculator, make sure you use parentheses appropriately, as I just wrote here, okay? Otherwise, the calculator will do the calculation wrong, all right? If you do that, you should get something like 67.8. Now, of course, we're doing a word problem, so we're going to use units, and this is feet per second, right? Feet per second is speed, distance per time. Okay, so that's just making that calculation a little bit closer, right? So instead of the 1 second gap that we did up here, where there's a pretty big gap from 52 feet per second average velocity to 84 feet per second average velocity, now we're narrowing that down and giving us a better estimate. Okay? All right, so that's what we're doing. All right, and you can see what they're doing here on the chart. They're just making these intervals smaller and smaller and smaller, and they see that average velocity is getting really close to 68 feet per second the closer we get to 1 second. Okay? All right, so that's the concept we're doing here, is we're going to start making that gap, that time gap in the calculation of the slope, smaller and smaller and smaller, and that's going to give us a much better accurate representation of what's happening at a specific time instead of over a time interval. All right, defining instantaneous velocity, and we're going to use the idea of a limit. So what I was just talking about is what a limit is. Again, we're going to bring those x values, or in this case t values, closer and closer together to get an accurate estimate. All right, so instantaneous velocity of an object at time t is defined to be the limit of the average velocity of the object over shorter and shorter time intervals containing t. Okay, and again, that's what we were just working on with that last example. Instead of doing 1 second intervals, we did 1/100th of a second interval. And you can see as they were doing on the chart, they went down to 1/1000th of a second interval as well. And the closer you get, the smaller you make those intervals and calculate the slope over that tiny, tiny, tiny interval, the closer you get to the actual instantaneous rate of change. Okay? All right, instantaneous rate of change of the function at A. So A, I know this is kind of a pain, they keep changing the variables on us. A is an x value. Okay, that's important. Oops, spelled it wrong. A is an x value. Okay, so they're saying the instantaneous rate of change of f, remember f is the y value, at A, which is an x value, also called the rate of change of f at A, is defined to be the limit. So again, limit means we're going to bring those intervals, those x intervals, closer and closer and closer together and calculate a slope. The limit of the average rates of change of the function, the y value, over shorter and shorter intervals around A, which is an x value. Okay, so we're making that gap between the x values teeny tiny and what something we would call infinitely small. Okay. All right, and this brings us to what a derivative is. The derivative of f at A, written with that symbol right there, that's f prime of A. So that little apostrophe looking thing means prime. Okay, again, when you see that, just means find the derivative of the function at an A value. Is defined to be the instantaneous rate of change of the function at the point A. Okay, this is a very important definition to understand. Okay. Now this one, talk about important. This is the key major. Look at all these stars. I know they're ugly stars, but it's just important. All right. When you see this word, derivative, you will think this word, slope. That's very, very important. It's a very deep concept. You need to understand that when you see the word derivative, they're asking for the slope. Okay? A little bit more specific, of course, than that, but that's the important part to understand. All right, so the derivative of a function at the point A, again, A is an x value, is equal to the slope of the graph of the function at that A value, that x value, which is also the slope of the tangent to the curve at that A value. Okay, both of those statements mean the same thing. So this is a graphical representation of what they're saying. Okay, so here, this first one here, visualizing the average rate of change of the function between A and B. Remember, A and B are x values. Okay, so average rate of change, we've done this before. We take that coordinate point and that coordinate point, do our little slope equation, and we get an average rate of change. But again, what if we want what if we want the slope of the line, in other words, the rate of change, at a specific point, not just between 2 points that are far away, but at a specific moment. All right, that's what we're doing here, right? We're going to keep bringing this B point. So this point here, B, we're going to keep bringing it closer and closer and infinitely close to A. And that's what they're doing here. So see how B is there and A is there. So let's bring B a little closer. Now a little closer. Now a little closer. Each time we bring it closer, we calculate the slope. Okay, so you think as we get infinitely close, if we were able to zoom into this slope infinitely close, let's say there's an infinitely teeny tiny space in between those 2 points right there, it's still 2 points. We can still calculate a slope. But that gap is so incredibly infinitely small, the difference doesn't make the difference does not make a difference anymore. Okay, it's such a good representation because it's so incredibly close to that point. Okay, that's what we're doing here when we find the derivative. All right, so estimating the derivative of a function given graphically, okay, by looking at a graph. So here's an example. For the function below, at what labeled points is the slope of the graph positive? In other words, what we're going to do is, so there's two ways of looking at this. When the slope of the graph is positive, it means the function is increasing. Remember we talked about that term, increasing function? As we go left to right on the x-axis, an increasing function means the y values are getting bigger, right? Okay. For a decreasing function, of course, as we go from left to right on the x-axis, the y values are going down. Okay, so that's important to remember. Increasing and decreasing functions. What is happening to the y values as the x values go to the right or get bigger? All right. All right, so first question here, let's see. What labeled points is the slope of the graph positive? In other words, increasing function. Okay, so let's look. Well, let's see. The y values are getting bigger from here to here. Now, at B, they're not getting bigger or smaller. That's something we'll talk about in a little bit, but it's not getting bigger or smaller. It's just staying. Well, you'll see it's actually 0, but we'll talk about that in just a bit. So we know at point A, right here, so the slope of the graph is positive at A. Let's see, but as we come over B, C is going down, right? Okay, so that's actually, I know that I should have separated these, I'm sorry. Negative slope, so decreasing function, so that's at C. As we come around here, though, we notice again the y values are getting bigger, increasing function, so positive slope at D. Okay, E again, like I said, that's a 0 slope, but we'll talk about that in a little bit. So as we come over here, we notice at F, we have a negative slope, a decreasing function. All right, so C and F have a negative slope. A and D have a positive slope. Okay. All right, and then another part of the question here, at which labeled point does the graph have the most positive slope? Okay, so think of most positive slope. So this line right here has a positive slope. This line has a more positive slope. And this line has an extremely positive slope. Okay, so that's what they're saying. So what point on this graph has the most positive slope? Okay, so let's look at that. What we're going to do is we're going to draw a tangent line at, well, so first of all, we know A and D have positive slopes, right? So let's draw a tangent line. Now I know it's not going to be perfectly straight, but it gives us an idea. Draw a straight line, tangent. Remember, tangent means it just barely touches the curve at that specific point. Okay. So there we draw a line, pretend that's a straight line. And then here we draw another straight line. That wasn't really supposed to cross through, but you get the picture, right? These are tangent lines. So which one has the greater positive slope? Definitely A, right? Okay, so most positive slope at A. Okay, and, oops. There we go. And then it's asking, what about the least positive slope? In other words, negative with the largest magnitude. In other words, again, just what we did with the positive, but the other way. So think, this line has a negative slope. This line has a much more negative slope. Okay? All right, so let's figure that out. So we know, we said C and F have negative slopes, so let's draw tangent lines on there again. Again, these are not perfectly straight, but they give us an idea. There and there. Again, pretend those are straight lines. Well, we can definitely see this one has a more negative slope. Okay? So F has the most negative slope. Okay? All right, moving on here. Let's see, estimating the derivative of a function numerically. All right, let's see example. Table gives P equals f of t, the number of households in millions in the U.S. with cable television, T years since 1998. So be careful how they write these. T years since 1998. So what that means is time 0 here is 1998. Okay? Time equals 2 means the year 2000, etc. Okay? Years since 1998. Okay, so first question here. Does f prime of 2, in other words, does the derivative or the slope at 2 appear to be positive or negative? What does this tell you about the number of households with cable television? So let's look at these numbers here. So we look at, if it's a positive slope, it's going to be an increasing function, an increasing y value, right? We just talked about that graphically above. So look at the numbers, the y values here, the p in this case, 64 to 66. That went up, didn't it? So there's definitely a positive slope between 0 and 2, t equals 0 and 2. What about this one to this one? Well, it's not much of an increase, but it is an increase. Okay, so we have a positive slope there, or as well, between 2 and 4. Okay, so we can assume, there's no guarantee because we would actually have to see more accurate data than this, but we can assume most likely between two positive slopes, you're going to have a positive slope. Again, it doesn't always mean that's the case, but in this case, the data kind of points to that. Okay, so definitely a positive slope. What does this tell you about the number of households with cable television? Well, P is the number of households. So as T is increasing, as the time gets bigger, the Y values are getting bigger, right? So the number of households with cable television is increasing over time. Okay, there you go. That's about all you got to write on that. Let's see, so at B, it says estimate f prime of 2 and f prime of 10. So in other words, the slope at 2 and the slope at time equals 10. So let me clean this up here. Okay. So in other words, what we're going to do is we're just going to find the slope. So f prime of 2, slope is derivative, right? F prime means derivative, is approximately, so squiggly equal sign means approximately. And what we're going to do, if we want to find, if we want to estimate the slope at 2, we're going to estimate the slope between 2 and 4. I'm sorry, we're going to calculate the slope between 2 and 4 to estimate the slope at exactly 2. Okay, so we use the slope equation, right? F of 4 minus f of 2 over 4 minus 2, right? Difference in the y values, difference in the x values. Oh, I should use proper notation here. Always use proper notation. We're not using f. In this case, we're using p, right? So p of 4 minus p of 2. And we plug in the numbers. You use these two coordinate pairs, right? All right, so we get 66.472 minus 66.250 over 4 minus 2 is 2, right? So if you do that, you get 0.222 over 2, which is nice and easy, 0.111. And of course, we do need to put units on this. So it's 0.111 millions of households per year. Okay, because this is a rate of change. All right, so it's a positive number, so it means it's going up, right? That's what so it says explain. Positive slope, positive derivative means increasing. Okay, so that one's increasing. Let's try f of 10, or I'm sorry, f prime of 10, the derivative at 10. This is going to be approximately, so we'll calculate the slope between 10 and 12. So f of 12 minus f of 10 over, 12 minus 10. All right, so that denominator is nice and easy. That's a 2. And we have 60.958 minus 64.274. And again, make sure when you plug into your calculator, use parentheses the right way. So if you punch this in, you should get negative 1.658. Again, same units here, right? Millions of households. I cannot write today. There we go. Per year. Okay. Now, what does this negative tell us? It tells us there's a decrease, right? So they're losing 1.658 million households per year. Okay? All right. So again, slope means derivative. Derivative means slope. Very important. Okay. All right, next section, 2.2, the derivative function. All right, so finding the derivative of a function graphically. So here's an example. Estimate the derivative of the function f of x graphed in figure 2.2. That's this graph here at x equals -1 and 3. Okay, so they have the graph here. So at f equals -1, that's right there. So notice what they did. They drew this tangent line in. Tangent is a straight line that crosses through the graph exactly once. Okay, and what they did was they used some points in there. Any 2 points you can find. You can find a point there. You could find a point there, and plug into the slope equation and calculate. All right, so again, derivative means slope. Okay, so the slope of that tangent line right there is 2. Okay, and then they did the same thing down here at f prime of -3, the derivative of the function at 3. So they drew this tangent line in here, used 2 points on the graph, plug into the slope equation, and they get a derivative of -1. Now let's look at these derivatives, because when you're doing math, you should always say, does my answer make sense? Right? Just like in life. Does this make sense? If someone says, hey, if you download this app, you'll be a millionaire overnight. Well, you should ask yourself, does that make sense? Of course, the answer is no. All right. But here, let's look. Does this make sense? A positive 2 slope. A positive slope means the function is increasing as we go from left to right. So that makes sense, right? Okay. Same thing here with the slope of -1. So that means negative slope means decreasing function, and we can definitely see the y values are dropping as we move from left to right. Okay, there you go. All right, so for a function f, we define the derivative function f prime by f prime of x equals the instantaneous rate of change of f at x. All right, in other words, we're going to find that slope. All right, here's an example. The graph of f is below. So this is the function, okay, f of x. We'll put some arrows on the end here. Which of these 3 graphs is the derivative of this graph? So we're trying to find which of these 3 is the graph of the derivative for this function graph, okay? So let me show you how you're going to figure that out. And I should have left you more room, and I do apologize for that. But what we're going to do is directly below this graph. So we're working with this graph. So ignore these guys for just a minute, these choices. All right. So we're going to draw a graph right. That didn't work. Right below this. Okay. Now this graph that we're drawing in is the slope, f prime of x, of f of x. Okay. So remember, slope means, derivative means slope. So if we have a negative slope, which we can see from here to this point here, we have a negative slope. The function is decreasing, so it's a negative derivative, right? So negative values are below the x-axis, correct? So it doesn't matter. This is just a sketch. So we just know, well, let's see. Okay, at some point we've got some negative values, and we're going to go up to, and I told you this before, but I didn't really talk about it too much. The slope at a minimum or a maximum, the slope of the tangent line, at a minimum or a maximum is always equal to 0. That's something we'll touch on a little bit later, but something to remember. So if the slope at this minimum right here is 0, that means the graph of the derivative must be 0, right? On the x-axis. Okay? With the y value on the x-axis. Okay, now we notice from here to this maximum, which again, this maximum means the slope's going to be 0 here. We have a positive slope. Now look at what's happening though. We have a increasingly positive slope here and a decreasingly positive slope here. In other words, draw some tangent lines in here. Let me clean this up so you can see better. Okay. Right here we have a small slope on this tangent line. Right here we have a larger slope on the tangent line, right? But somewhere in the middle here, these slopes start getting smaller and smaller again, and of course we said at the maximum there the slope is 0. So we're going to graph that in, right? So we're going to say the slope's getting bigger, bigger, but then smaller, smaller, and back to 0. Okay, based on my tangent lines there. I know this is a pain, so you're going to have to probably watch this several times. Okay, now we know from, so 4 down here, we don't know where this graph really ends, but we just know after x equals 2 here, we have a decreasing function. And again, these slopes are getting more and more and more negative, okay, of the slopes of these tangent lines. So we just know the graph is going below the x-axis, getting smaller, the graph of the derivative. Okay, so now based on our wonderfully accurate sketch, it's not accurate, I'm just being, well, trying to be funny anyway. That's the shape of our derivative of this function. So the only one of the three that even kind of sort of represents or matches that is C. Okay, again, we have starting with a negative slope, getting less negative, becoming 0 at that minimum. Then these slopes get more positive, then less positive, and back to 0 at that maximum. And then less and less more and more negative, right? So we have negative slopes going down this way. Okay? Again, you might want to watch that explanation a couple times. It's kind of complicated, okay? But it is important to understand. Okay. What does the derivative tell us graphically? I've been mentioning this several times now. These are extremely important to know, these 3 facts. If f prime, that's your derivative is positive on an interval. Now when they say on an interval, they're talking about x values. Interval of x values. Okay? If the derivative is positive on an interval of x values, then the function is increasing. The y values are getting bigger on that interval of x values. Okay? Positive slope, positive derivative means increasing function. Of course, we can just switch it all around. If our derivative is negative, that means the slope of the tangent lines are negative on those x intervals, then the function is decreasing. The y values are going down. And if the derivative equals 0, if the slope equals 0, because think slope of 0 means flat line, right? Not increasing or decreasing, like what happens at a maximum or a minimum, okay, on the function. So 0 slope, 0 derivative, the function is constant on that interval. In other words, you have either a maximum or a minimum on the function, okay? All right, so the magnitude of the derivative gives us the magnitude of the rate of change of f. So magnitude just means bigger or smaller. So that's like I was talking about before when we drew that graph of the derivative. More negative, less negative, more positive, less positive magnitude. All right. If f prime, if your derivative is large in magnitude, then the graph of the function is steep. Okay, and it's steep up if your derivative is positive or down if the derivative is negative. If f prime is small in magnitude, the graph of f is gently sloping. Okay. All right, estimating the derivative of a function given numerically. So here's an example. The table gives us gives values of c of t. All right, so think of that as your y value. This is your x. Time is your x value. The concentration in micrograms per cubic centimeter of a drug in the bloodstream at time t in minutes. Construct a table of estimated values for c prime of t, the derivative, the slope, the rate of change of c of t with respect to t. All right, so we've done this before. In other words, we're going to calculate the slope between 0 and 0.1. Okay, let's do that first. So c prime of 0, we use these 2 points, right? We've done this before. So we'll do 0.89 minus 0.84 over 0.1 minus 0, right? Change in c over change in t. Punch that into your calculator. Again, use parentheses appropriately. Be careful with those parentheses. And we should get 0.5. So right here, the derivative is estimated at 0.5. Now you're just going to continue doing this. I'm not going to keep writing them out because it's the same calculation, or different answers, but same calculation through the whole thing. So to get the next one here, you check the slope between these 2 points, right? Which actually is, again, 0.5. All right, and then we just keep doing the same process. So between 0.2 and 0.3, you'd get a 0.4 slope. So try some of these out. You don't have to do all of them, but try them out. Make sure you're getting your calculations correct. And I'm going to just fill in the rest here so you can check your answers. Oops, last one should be 2. There we go. Okay, so of course what we can see is we have an increasing function up until this point. The derivative is 0, so we have either a maximum or minimum. I'll show you how to figure that out in a second. And then a negative slope, negative derivatives here. So just think, if we're moving from left to right, from here we have positive, right, slope, so positive slopes, then our 0 slope. That's, in this case, is going to be a maximum because then it goes to negative slopes, decreasing. So whenever you go from positive to negative, positive derivative to negative derivative from left to right, you have a maximum. Okay? All right. So here's an example using thinking of derivatives and stuff like that in terms of real-life applications. So a vehicle moving along a straight road has a distance f of t from its starting point at time t. So which of these 3 graphs fit these 3 situations here? So let's think about it. All right, first one here, A bus on a popular route with no traffic. Okay, so no traffic means, it's going to accelerate, to its maximum speed, and then, but it's a bus, right? So what is it going to keep doing every so often? It's going to slow down and stop for passengers, right? So this one would make sense, right? So it starts off, it gets to some speed and maintains that speed, and as it approaches its next stop, it slows down and stops, right? And stays stopped for a few minutes to load and unload, starts up again, gets to some, regular speed, slows down at the next stop to unload and load, right? So this one here, I think this would be A. Okay, a bus on a popular route with no traffic. All right, let's see, what about B? Car with no traffic and all green lights. Right, well, this one will make sense, right? You start accelerating and you get to a certain speed, right? And you just keep going at that speed till you get to your destination because you have all green lights. Although some of us would probably do this, right? No, I'm just kidding. All right, little math joke, sorry. All right, so that's B. And, well, I know we know the last one is C, but of course, let's analyze it. A car in heavy traffic conditions. This is driving on those darn Southern California freeways, isn't it? Speed up, slow down, speed up, slow down, speed up. Oh, all over the place, right? Okay, so this would definitely be traffic conditions. Okie dokie. All right, moving on. Section 2.3, interpretations of the derivative. All right, so we've already talked about the derivative. The derivative is the slope of the tangent line on a curve at a given point. And we use this notation, f prime of x. right? There's an alternate notation, and that's this one here, dy dx. That's how you state it, dy over dx, but we state it dy dx. Okay, and the way you want to think about saying this is, this means the derivative of y with respect to x. That's how we say it, the derivative of y with respect to x, dy dx. Okay? All right, so using units to interpret the derivative. So the units of the derivative of a function are the units of the dependent variable. So dependent is the y variable, divided by units of the independent. Independent is x. In other words, the units of dA dB are the units of a divided by the units of b, right? Or as we wrote it up here, dy dx, units of y divided by units of x. If the derivative of a function is not changing rapidly near a point, then the derivative is approximately equal to the change in the function when the independent x variable increases by 1 unit. That's usually how we read a slope. Example, the cost of extracting T tons of ore from a copper mine is C equals F of T dollars. What does it mean to say that F prime of 2,000 equals 100? I know it's hard to see. There's a little prime right there. Okay? So that says when 2,000 tons of ore have already been extracted from the mine, the cost of extracting the next ton is approximately $100. Okay, because the function is cost. All right. All right, so that's important to understand how to interpret these things. Let's see, another example. If the velocity of a body at time t seconds is measured in meters per second, what are the units of acceleration? Okay, so acceleration, which we use A for acceleration, is speed per time, right? We know that's a change in speed per time, but the units are speed per time. So speed is, we just said right here, meters per second, and time is seconds. So meters per second, we can write like this, meters per second squared. That's the units for acceleration. Okay? All right, next. Using the derivative to estimate values of a function. All right, tangent line approximation, local linearity. Linearity means straight line. All right, so if y equals f of x, that's your function, y equals f of x, and delta x, the change in x, is near 0, then delta y is approximately the derivative times the change in x. Okay? For x near a again is an x value, we have delta y equals f of x minus f of a, and delta x equals x minus a. All right? This is just a manipulation of the derivative slash slope formula. So f of x is approximately f of a plus the derivative at a times the change in x. Okay, so that's important to understand that. All right, so let's see. Example. Annual net sales in billions of dollars for the Hershey Company is S equals F of T of time T in years since 2010. So again, be careful with T values here. Interpret the statements F of 5 equals 7.39 and F prime of 5 equals negative 0.03 in terms of Hershey sales. Okay, so F of 5 means in 2015, right? Because years since 2010, 5 years since 2010 is 2015. Sales are 7.39, and we need units, billions of dollars. Boy, I'm in the wrong business, aren't I? That's okay. I love this more than chocolate, I promise. And then the next one here, f prime of 5. So f prime of 5, in other words, the derivative of the function at x equals 5, or t equals 5 in this case, is negative 0.03. So this means in 2015 to 2016, over a 1-year change, right? Because derivative means change. Let's see, so from 2015 to 2016, sales of chocolate, well, it's a negative slope, negative derivative, so they decline by that number, by 0.03 billion dollars. Okay? The poor chocolate people, they're all poor now, right? All right, B, estimate f of 8 and interpret it in terms of Hershey sales. All right, so we're going to use this formula that we have above here. All right, so f of 8, so we're going to say, so we're estimating, so we're going to use the same derivative as f of 5, f prime of 5. All right, so f of 8 equals the 7.39, right? So that's f of a, minus 5 times negative 0.03. All right. Oh, my mistake. Yeah. I accidentally erased the negative there. There we go. Okay, so we're good. So let's see, I think I made a calculation error in my notes. So let me recalculate that. Give me 1 second here. So let me see. So 7.39. All right, so this should be 7.54 billion in sales. Okay. All right, and that's in 2008, because f of 8 is 3 years past 2015. In 2018. Okay. All right, let's see. Next, relative rate of change, y equals f of t of y equals f of t at time equals a. So time and a are x values, is defined to be the relative rate of change of y at a dy dt over y. So in other words, the derivative at that specific a value divided by the function value at that a value. Okay? All right, so let's do another example here. All right, let's see. The number of active Facebook users hit 1.55 billion at the end of September 2015. So we can see there's a data point there. And 1.59 billion at the end of December. With t in months since the start of 2015. So in other words, January is 1, February is 2, December is 12, etc. Right? Let f of t be the number of active users in billions. So estimate f of 12 and f prime of 12 and the relative rate of change of f at 12. So we're going to use this formula here at the end. Okay? All right, so let's write out our coordinate points here. So September, the coordinate point is going to be 9, 1.55, right? Because September is the 9th month, and they said 1.55 billion. And then December is 12, 1.59. Right? December is the 12th month, 1.59 billion. So f of 12, so what this point actually interprets to is f of 12 equals 1.59. Okay? So we got that. There's f of 12. Now f prime of 12, so let's do this calculation here. So f prime of 12 equals, so we're going to use the slope formula again, right? Using these two coordinate points. All right, so then we do 1.59 minus 1.55 over 12 minus 9 punch that into a calculator, again, use parentheses appropriately. And if I did my calculations correct, it should be 0.013 billion. Now, since it's positive, right, 0.013 is a positive number, it's a $0.013 billion increase, right? There we go. In users per month in this case. Oh, we should say that. Increase in users per month. Okay. All right, so we found f of 12, we found f prime of 12. Now they want the relative rate of change of f at 12, t equals 12, which is that formula right up there. All right, so relative rate of change equals f of a over f prime of a, which in this case, a is 12. And we got those two numbers up here. So we got 1 point, oh no, I think I did that backwards, didn't I? Yep, derivative on top. Oh man, I messed up. That's okay. Mistakes happen. All right, so we've got, let's see, 0.013 over 1.59. Punch that into your calculator, so 0.008. Or, to make it mean something more, 0.8%. Okay, 0.8%. Watch converting from decimals to percentages. Okay, so that's some good information there on the first derivative. First derivative tells us increasing and decreasing function values. Section 2.4, what about the second derivative? So the second derivative is the derivative of the function. Does that make sense? It's just you take the derivative again, but use the derivative coordinate points to find the second derivative. Okay? So double prime means second derivative. Actually, let's see. Right there. Second derivative. Okay? F double prime means second derivative. If the second derivative is positive on an interval, remember these intervals are x values, then the first derivative is increasing and the graph is concave up. Concave up means that shape, the concavity, the curvature is upwards. Okay? On that interval of x values. If the second derivative is negative on the interval of x values, then the derivative is decreasing and the graph is concave down on that interval. Okay? All right. So that's what they're showing you here, these pictures. All right? So notice right here, right? So from here to here, so be careful with concavity and increasing, decreasing functions. It gets kind of confusing. So through this whole interval here, this entire interval, the second derivative is positive. Okay? But from here to here, the first derivative is negative because the function is decreasing. But from here to here, the first derivative is positive because then it's increasing. Okay? Let's see. Same thing here, or just going the other way around. Through this whole interval, the second derivative is negative, concave down. Okay, but from here to here, positive derivative because the function's increasing, and negative derivative here. Okay? All right, so let's do an example. So we're going to plot this graph. We're going to fill out this graph. So at exactly 2 of the labeled points in the figure, the derivative f prime is 0. Second derivative f double prime is not 0 at any of the labeled points. On a copy of the table, give the signs, so positive, negative, of the function, first derivative, and second derivative at each marked point. Okay? So this is the function. So this curve is the function, right? This is our x-axis. Of course, this is our y-axis. So let's look at the function values first. Okay, so anything above the x-axis is positive. Anything below the x-axis is a negative function value. So point A, it's definitely below, right? So is point D below the x-axis? All right, so we have a negative there, and clearly B and C are above the x-axis, so they're positive function values, okay? All right, now let's do first derivative, f prime. Okay, so that tells us increasing or decreasing. Now it said right here, at exactly 2 of the points, the derivative is 0. Remember, that occurs at your maximums and minimums. Well, we can see right here, A is a minimum and B is a maximum. Okay, so A and B are 0 slopes, 0 derivatives, because they're maximums and minimums. C, if we draw a tangent line through C, we know we have a negative slope. And if we draw a tangent line through D, we have a positive slope on that line. Okay? All right. Now let's look at the second derivative. So that's concavity, that's curvature. So at point A, the graph is curving up. So it's positive. At B, curving down, so negative. At C, the graph is still curving downwards. Okay, so be careful. That's still a negative. And at D, we have this upward curvature. So positive second derivative. Okay? Go over this a few times, because these 3 different things, the function value, the first derivative, and the second derivative, can get very confusing. All right, another example here. So population P, growing in a confined environment, often follows a logistic growth curve, like the graph shown below. All right, so describe in terms of the first and second derivatives how the rate at which the population is increasing changes, how the population is increasing changes over time. Okay, so the first derivative. All right, let's look at that first. So the first derivative tells us if the slope is, or if the function is increasing or decreasing. So we can see, so I'm going to add some points in here. So right about here, we're going to call that A. Okay. So from, and of course we'll call this 0. All right. So from 0 to A, the L, the function value, is increasing, right? So which means a positive slope, which means positive derivative. So we're going to say first derivative from 0 to A. This is interval notation. These are not coordinate points. This means from 0 to A. Let's see, L prime is positive, right? The derivative is positive, greater than 0. Sorry, my handwriting's pretty bad here. Let me write that better. L prime is greater than 0. Okay? Now from A on, right? In other words, from A to infinity, it looks like the derivative is 0. Oops. L prime equals 0 because it's flatlining. Okay? All right. So that tells us we have, what was this about? Which just says population. So population is growing from 0 to A, but remains constant from A to infinity. Okay, that's what the first derivative tells us. Okay, now sorry, I'm going to kind of squeeze it in here. Second derivative. All right, so let's see. Using these intervals. Now remember, the second derivative tells us about concavity. Okay, so curvature. So from 0 to T star there, what is that curvature? The curvature is up. So L double prime, the second derivative, is positive. Okay? But then from T star to A, we have a downward curvature. So from T star to A, the second derivative is negative, right? Concave down. Now from a to infinity, we don't say second derivative is 0. That's something we'll probably touch on later, but we don't say it's 0, it's just no increase. Okay? Okay. Okay. And we just went through this. So this is just showing you notation. I know this one's kind of weirdly written. It's easier to see it as a stacked fraction. D squared P over dt squared just simply means second derivative of P with respect to T. Okay? So when you see that, it means second derivative of P with respect to T. And we already went through those signs, right? So what is the sign of the second derivative? Right here. Positive from 0 to T star and negative from T star to A. Okay? All right. So what is the practical interpretation of T star and L? So L, you'll notice at L, that's what's called the carrying capacity. Carrying capacity, in other words, it's the maximum the environment can support. Right, so that goes for biological growth, also sales, business, etc. Okay, T star is what's known as an inflection point. Okay, it's an inflection point. It's the point where concavity changes. So at this point right here, this T star value, we go from curved up to curved down. Okay? That is also known as the fastest increase, point of fastest increase. Okay, that's where your first derivative is going to be the highest on that interval. Okay, so again, an inflection point is where concavity changes, right? The curvature changes. Okay, last section here for this chapter. Marginal cost and revenue. All right, so graphs of cost and revenue functions. So quick example here, if cost and revenue, so cost of course is how much it costs you to do something, run a business, whatever, manufacture a product, etc. Revenue is how much money you take in, right? So sales basically, are given in this graph. For what production quantities, right, X values, does the firm make a profit? So of course, when you take in more than you spend. So when revenue, all right, so when revenue is greater than cost, that's when you're making a profit. Okay? All right, and you can see that happens here between these 2 points, right? The revenue graph has a higher dollar value than the cost graph. Okay? So from 130 to 215 quantity of whatever this product is. Okay? All right. All right, so marginal analysis. So suppose C of Q is the cost function of running Q flights for an airline. If the airline had originally planned to run 100 flights, its cost would be C of 100. With the additional flight, the cost would be C of 101. In other words, one more flight, what would it cost? All right, so marginal cost is the difference between the 100th and the 101st cost. I mean, it doesn't have to be 100 all the time, but you know what I mean, right? So now C of 101 minus C of 100 actually is the slope. All right, it's the average rate of change of cost between the 100th and 101st flight. Okay, So that's important. So here's some terminology to understand. Make sure you know this stuff. So marginal cost, they write it as MC, is C primed of Q. In other words, it's the first derivative of cost. So marginal cost means find the derivative of cost. Okay? So marginal cost is C of Q plus 1 minus C of Q. In other words, the cost of doing, or the average rate of change of cost of doing one more unit of business, whether it's flights, cars, whatever they make. Okay? And marginal revenue is R primed of Q, is the derivative of revenue. So what you're going to want to remember, anytime you see the word marginal, mathematically you're going to think derivative. Okay? All right, so let's keep going here. All right, so here's an example. So the cost and revenue functions for a charter bus company are shown here. Should the company add a 50th bus or a 90th bus? What do you think? Well, let's look here. So profit is when revenue is bigger than cost, right? So let's see. First one is, should we add a 50th bus? So from, I know it's kind of hard to see, but let's say there's the 49th bus right there, and here's the 50th bus. The gap between the revenue and the cost here is much bigger, right? Right, so bigger gap between revenue and cost, especially when, well, not especially, but when revenue is bigger than cost and you have a bigger gap, vertical gap, you have more profit. So yeah, it's worth it to add a 50th bus because you're going to gain more profit, okay? Not just more profit, but a larger margin of profit margin. But what about the 90th bus? Let's see, 90 is, I don't know, somewhere in here, right? What's happening to that vertical gap between revenue and cost? It's actually, it looks like it's getting smaller than when it was at 50, right? Okay, so we would not want to add a 90th bus because at some point we're starting to decrease our profit margin, okay? Again, it depends on the whole business picture. Of course, this is just mathematically speaking, okay? Because what happens is, in real life, if you have a good business going, strong business going, even though these profit gaps, the profit margin gets smaller, you're doing more volume. So it just depends, right? There's other things you got to look at in real business. This is just looking at the mathematics of it. All right, example 4. If the revenue and cost functions are given by the graphs below, sketch graphs of the marginal revenue and marginal cost functions. All right, so they already did it here, but let's analyze it, right? So this is the revenue. It's a straight line, so it has a constant increase. In other words, no matter where we draw a tangent line to that curve, it's always going to be the same line, a straight line with the same slope. So that's why this is a horizontal derivative, right? The graph the function values of the graph are increasing at the same rate throughout. So the derivative stays constant, flatlined throughout. Okay? Revenue is increasing at a constant rate, then the derivative remains constant, flatline. Okay? All right. So now this one here for cost, right? We can see it's increasing the whole time, right? So it's going to be a positive slope. It's going to be above the Q-axis, above the X-axis in this case. But we're talking about more and less positive, right? Like we did before when we drew the graph in. Draw some tangents in here. So this one has pretty big positive slope, right? So that's what we're talking about here. Big positive slope. As we come across here and here, it's still a positive slope. It's still increasing, but it's getting smaller, but still positive, right? Still above the Q-axis here. As we come around that change, right, again, we can see these slopes getting more positive. Okay? So that's important stuff to understand. All right? And that's it. That's chapter 5. Oh, I'm sorry, that's chapter 2. Thank you very much.